Hi, welcome to lecture 10 for our Introduction to Computer Science course. Today we're going to be talking about computer graphics. Now, I want to preface this lecture by saying, please don't get frustrated. There's a lot of stuff in here that is just to wash over you and not for you to understand every single aspect. It really goes a little bit more in depth than I would like. So most of the questions that I have come from the first like 3 sections. So anything beyond that is kind of just bonus material. So that being said, I'm going to go ahead and get started with today's lecture. So we are going to go through sections 1 through 4, and then we're going to skip to section number 6. We're skipping 5. Like I said, most of the questions are going to be coming from sections 1, 2, and 3. So hopefully we can get through this chapter together. And again, like I said, I know this chapter is going to be difficult. There's going to be a lot of new terminology, but please don't panic. So when we talk about computer graphics, there are 2 different ways that we can talk about graphics. We can talk about it in 2D or 3D. So 2-dimensional graphics or 2D graphics, that is going to be more of a flat image and what we are more used to seeing in, like, say, a photograph. A 3D graphic, now we're starting to deal with manipulations of all 3 dimensions while we're trying to display any kind of image. When we're going into 3D graphics, we are starting to go more into virtual scenes. Okay, so it's not just a flat picture anymore, but there is a depth to it, and it is more immersive when we're looking at 3D. Now, 3D graphics, there are 3 different terminology points that I want to point out to you. Modeling is the designing and the construction of your digital scene. Now, rendering is applying mathematics to project these 3-dimensional objects onto a flat surface in order to be able to store them as an image. So the rendering is the creation of that 3-dimensional object in that 2-dimensional plane. Lastly, displaying is real-time viewing, if we're talking about video games, or transfer to some permanent storage, whether it be a motion picture or how your user is actually going to see it. So we have an example here in this image where you actually have an object in a scene that is a 3-dimensional object, and you can see here it is spherical in nature, so it is a 3D sphere. Now, what we want to have here is an image window in which we are going to take a projection of that 3D and make it onto that 2D environment of that projection plane. So really, when we're talking about modeling, we're constructing the scene. Rendering is actually making it go from 3D to 2D using mathematics, and the displaying is how we see it. Now, in order to model objects, there are 2 different things that we look at. We look at shape and we look at surface. Now, the shape is traditionally represented by some sort of polygon mesh. Okay, typically it comes from either mathematics or curves and surfaces or procedure models. Or other methods that are out there. But the shape is going to give basically a rough estimate of what the geometric qualities of an object is. Now, surface, on the other hand, can be represented by a texture map, and you're going to take that shape and you're going to take it to from that 2D into that 3D. So your surface is what is going to allow that mesh to become uniform and to kind of have that look like there's actually a planar surface on there. For example, a shape here this right here is a polygonal mesh for a sphere. Okay, so you could see there's going to be points and lines, and it's going to give the representation of a shape. On the other hand, we can take that shape into existence by using things called Bezier curves. And so this is going to create control points marking the start and the end, and then allowing a curve to happen in between them. Now, for example, if we want to grow a polygonal mesh for a mountain range, we start with our typical triangle shape. From those triangles, we connect midpoints, okay? So for A and B, we both have a two-dimensional object being shown. See, now we're moving into that three-dimensional realm. We're moving these midpoints out to give it depth, okay? And then we basically rinse and repeat. So every time we connect these midpoints, the midpoints are all connected. You make an additional triangle and then pull that triangle, either push it in or pull it out to show some depth. Now, rendering, remember what rendering is? It's that mathematical equation of how we get the lines. There are two different ways that we look at that, reflection and refraction. Now, reflection is when the lights bounce off the surface, okay? And when we're talking about light, we can, any kind of light, diffuse light, ambient light, but it's a reflection off of the surface. Whereas refraction is the light that's penetrating the surface. So just to reflection, it's like it reflects off of a mirror. Refraction, it basically soaks up those light rays. So here, for example, this is reflected light. Remember, it's like bouncing off of a mirror. The light source comes in at some angle and it bounces back off in an equal and opposite angle. Now, here is our sphere, and we've now applied a surface to it. And you can see the difference between this one and the mesh that we saw a couple slides ago. Much smoother all around. You don't have those points and lines. There are some things, you know, this is really talking about shading more. Your specular light is where your light source is going to be, and your diffused light is where it kind of diffuses out from that center point. You can see how the integration, though, of this light and these different light sources are what help give it that three-dimensional shape. Okay, it's still a two-dimensional object, right? But you're giving it a three-dimensional shape by using the light, reflection and refraction. Now, refracted light, on the other hand, you can see this is a very different picture than the reflected light, right? So you have a light source coming in, and some of it is absorbed by the shape. So here we've got the refracted ray going down and to the right. There's an angle of refraction, and the boundary into the materials is the blue part on the bottom. So based on where it's refracting, we can give it shading, and we can give it different aspects to give it that three-dimensional shape. Now, the rendering pipeline. These are some things that we use in that rendering process to create that 2D/3D image. So first thing is clipping, and this is going to restrict attention to objects within the new volume. So anything outside of the view is just taken away. Scan conversion, this is going to associate the pixel positions with different points in the scene. So if you are to approach, say, a tree is in a location, and the closer you get to that location, the bigger the tree gets. Hidden surface removal, this is getting rid of anything that is blocked from view that your user doesn't need. And then finally, shading. This is going to determine the appearance of how your points look, but at this point for the shading, you're associating it with those pixels. We did talk a little bit about pixels and how those are all those little tiny sections. So the shading is going to be how that gradient goes across this two-dimensional image to give it that three-dimensional look. There are three different shading techniques that we're going to look at. There's a flat shading, a Gouraud and Phong shadings, or bump mapping. Now, flat shading is going to be the most basic of types. You're going to take that mesh and you're just going to apply a surface to it. Now, the Gouraud and Phong shading is going to be much smoother and rounded in appearance. And the bump mapping is actually going to be a little bit bumpy. I think I have some examples of all of these. Yeah, here we go. Flat shading. So you can see this looks very similar to what that mesh looked like when we were talking about the sphere a minute ago. The sphere, every one of those little boxes in the sphere was given just a flat surface. Each one of those little boxes is a single pixel. And you can see how it is kind of boxy and not very smooth and rounded. As opposed to your Gorad and Phong shadings, you can see there's slight differences between them. They are still very, very similar. The Phong to me is a little more like balanced, because when you look at this light source right here, it is nice and shaded, and it kind of disseminates very quickly. Whereas in the Gorad over there on the left, it's a little bit more choppy. But it is a much different view than what we just had previously in the flat shading. Finally, the bump mapping. What this is doing is it's taking each little block and creating surfaces within them. Again, this is going to give a lot of texture, and there's going to be a lot of changes within it, but it may not be that smooth, rounded look that we're looking for. But it is a good look because, say you're modeling something that resembles brick or stone. This might actually work a little bit better because those surfaces are not going to be nice and smooth to begin with. Rendering pipeline hardware, there are a few different things that we use when it comes to computer graphics. We have a graphics card, which is going to be attached to the computer's bus system. And typically, this is what your monitors plug into on your home computers and things like that. The other thing that we do have is a graphics processor unit, or a GPU. This is specialized for graphics. It's going to allow for very fast graphics computations and renderings and redraws, and it can be programmed to perform non-graphic calculations. So even though you have a GPU, you don't actually necessarily need to use it for graphics. One other thing is local lighting versus global lighting. Now, the local lighting model does not account for light interacting among objects, okay? Which means if you have one sphere and you've got a light on that sphere, it's only dealing with that one sphere at a time. Global lighting, on the other hand, is going to account for interaction between objects. So if you have two spheres, and one is blocking the light of the other, in global lighting, it is going to reflect that. So for global lighting, we use things like ray tracing and radiosity. Local lighting is usually sufficient when you're dealing with a single object or objects that may not have any interactions between them. Global is more for when you're in an environment that you want things to interact, cause shade, cause light within each other. Last but not least, our last slide for today is for simulating motion. There are two different methods that we use, dynamics and kinematics. Dynamics is basically using the law of physics to determine where objects are, how they move, when they should move, as opposed to kinematics. Now, kinematics is when you program into those images things like joints and appendages to determine the position of the objects. Here in kinematics, we're looking at more at like avatar movement, whereas dynamics might be just a spherical ball falling, for example. So for kinematics, we are going to look at things like I think this is to be avatars and motion capture, because a human might walk or sit or stand. They don't really apply using the laws of physics. They use the laws of kinematics. You've got knees, you've got elbows, you've got joints, and you've got muscles that help you sit and stand and dance and things. So that's where those two different simulations come into play. Again, very short lecture. It's not easy stuff. I really hit the highlights and the things that I think maybe should just be what's important. There is a lot more in the book and in the chapters. It does go a lot further in the weeds than I would like, but feel free to take that jump into the weeds. So that is all I have for today. Thank you so much for watching the video. And as always, if there are any questions, comments, concerns, please do not hesitate to email me. Bye.